welcome everyone to today's webinar. This is the number 8 webinar series organized by ANEN, the Asian Network for Education and Training in Nuclear Technology, in collaboration with IEA under the TC project of RAS 0091, strengthening NST education at the secondary and tertiary level. So this year, ANEN is continuing its celebration of its 20th anniversary, and part of it, as with its motto, where ANEN is where we learn and share nuclear knowledge, ANEN and its members are sharing nuclear knowledge, nuclear technology in various different areas where nuclear technology contribute to the benefits of the modern life. Today, we are grateful to have two prestigious scientists from Iran, Professor Muhammad Ghanadi and Dr. Simidox Shirwani, who will be sharing their expertise on the title Radiopharmaceuticals in Human Health. This session today will be moderated by Dr. Yasir Kasizas, one of the ANEN Steering Committee members, and also in the Nuclear Science and Technology Research Institute in Iran. My name is Marina Mishar. I'm the session head for the Technical Cooperation Division for the Asian and Pacific region, and also managing this TC project RAS 0091 on NST education. And I'm pleased with the initiative spearheaded by ANEN to continue to share and make it regular at a monthly basis to share various webinar series in different topics. So without further ado, I would like to give the floor to Yasir, the moderator of today's webinar, to take on the session onwards. Yasir, you have the floor.
Thank you, Marina. Hello and good morning from Tehran. On behalf of the Asian Network for Education in Nuclear Technology, I would like to say welcome all of you to today's webinar. This is a part of ANEN webinar series for 2024, which have been organized with the IEA support. As mentioned before, the topic of today's webinar is about radiopharmaceutical in human health, which is the most important application of nuclear technology in our daily life. We have two invited speakers from Nuclear Science and Technology Research Institute of Iran. The first speaker is Professor Muhammad Ghanadi, which is the outstanding Iranian scientist in the field of radiopharmaceutical. And the second speaker is Ms. Dr. Shirwani. She is Associate Professor of Chemistry and has been working on separation and purification of radioisotopes for medical purposes. So I would like to invite Professor Ghanadi to start his speech. Professor Ghanadi, the floor is yours.
Bismillah ar-Rahman ar-Rahim, in the name of God, the compassionate, the merciful. Good morning for West, good evening for East, and good day for middle of the world. My name is Muhammad. I'm a research fellow from Nuclear Science and Technology Research Institute. I would like to have some explanation about radiopharmaceutical in general. After me, Dr. Shirwani will talk to you about this pharmaceutical science and technology. Well, as you know, first I would like to say what is radioisotope, because it's a general meeting, so I want to talk a little bit about the general information for you. What is radioisotopes? Radioisotopes are isotopes of elements which are radioactive, so they are called radioisotopes. In these days, radioisotopes play a big role in the life of the human. Industry, medicine, agriculture, ecology, and environment. But because of the But because of the speaking of today, I would like to say something about radiopharmaceuticals. Well, radioisotopes in medicine play a fantastic role for the human life, for diagnosis of their diseases and therapy also. If we can look this picture, it is very clear what the radiopharmaceutical comes from a radioisotope and becoming a radiopharmacy in the industrial manufacturing places. And after quality control, it goes to the human body. In human body, it goes and sits in a place which we want to see what is happening there. For example, for his heart diseases or for cancer diseases. Well, this is the role and the root of the radiopharmaceutical for human, for example, for the cancer diagnosis for him. For this purpose, radioisotopes can decay in many passes. For example, if we say some radioisotopes or radionuclides can decay by alpha particles, which means that it will be helium for us after its decay. Alpha particles are very important. I will talk to you about them. Beta particles, which is similar to electrons, but it comes from the nucleus of the radioisotope, and gamma emission. This is the main decay series. But also we have internal conversion, and also we have electron capture, and we have also usual electrons. But mainly we discuss about these three decays of radioisotopes. Well, radiopharmaceuticals are medical formulation containing radionuclides, which are safe for administration in human for diagnosis and therapy. I would like to say something to you, very simple one. If you can imagine that one person carrying something with himself, which it is always with it, anywhere he goes, that thing will go with him. For example, if he goes in the mountain, near the river, in the road, it will go itself, with himself. So if we can imagine that the radioisotope is that thing which is being carried, and also the man who is carrying it. So radioisotopes are with some chemicals, which it means that the chemicals go to some places in the body and sits there. It's only carrier. It doesn't do anything else. Radioisotopes starting giving some particles or photons in that place of the body, so we can inspect in it. We can get some pictures from it, and also if we can wish it will be okay with that radioisotope. Maybe, for example, knowing the kind of cancer in his body. So a radiopharmaceutical composed of two parts, one radionuclide and one pharmaceutical. You can see in this picture very nice. This is a radioactive compound. It will link with target molecule, and this molecule goes to the cancer place there. So three parts of the work can be done: biological agent, linker, and the target. The purpose is the target of that radiopharmaceutical, where that pharmaceutical should go. For example, kidneys, stomach, thyroid, brain, or anywhere we want. Can you see this one? The various radiopharmaceutical therapy constructs to deliver radiation. That's the radiation can do therapy in the cancer place there. Just you can see that atom radioisotope goes inside the place there, and also you can go like small molecules or like peptides. We have actually 3 kinds of radiopharmaceutical. Some pharmaceuticals are only elemental. For example, they are inert gases like xenon-133, radium-223, or krypton-85M. This is just only elemental. Secondly, very simple radiopharmaceutical. For example, sodium iodide as radioactive iodide, which it can go to thyroid and sit there. Some radiopharmaceuticals are very complicated, and they link with kits and very big compounds and go to the places which we want. So 3 kinds of radiopharmaceuticals we have. In this picture, you can see the radionuclides. Actually, we have 3 kinds of radionuclides. Natural one, which are from the beginning of the Earth, for example, uranium, and also radionuclides which can make it, they are artificial. Radiopharmaceuticals are built and constructed by radionuclides which are artificial and man-made, and they are very important here. Actually, there are more than 2,000, maybe 2,200 artificial radionuclides. Some of them are beta minus decay, some of them beta plus or electron capture, and some of them decaying by photons or gamma. So this is the explaining how radionuclide decays, the root how decays. For example, what is beta particle? And alpha particle and our electron. You can see the emission energy per decay like that, and emission energy per decay for alpha particles, and emission energy per decay for electrons. This is called Auger electrons. Auger electrons very important, but they don't have very big and very large energies. But betas and alphas have much energy. For example, alpha particles you can see from 5 to 9 MeV, beta particles from 50 to 1,300, but Auger electrons that have very small amount of energies. So how do we produce radionuclides for these radiopharmaceuticals? You can see here 3 kinds of routes we can produce radiopharmaceuticals or radionuclides. First of them is accelerators, which can accelerate protons or neutrons. It is used for producing some amount of radionuclides. For example, gallium, thallium, krypton, indium. But the main facility for producing a radionuclide is a reactor, which we can use neutron there for producing radioisotopes or radionuclides by neutron gamma reaction. And also we have the fission. Fission also is in the reactor, fission of uranium. But how do they produce radionuclides? We will say in this picture. Very brilliant picture is this one. By permission of internet, we have got this picture from internet. I'm explaining a little bit for this picture for you. Well, maybe you know that uranium is a natural radioactive element. It is created by the creation of the Earth. Because it has so long half-life, it is existing just now. Uranium is a metal, it's in the periodic table, but it is not the same as iron, copper, tin. You cannot make anything with it. For example, car, bicycle, motorcycle, ship, anything. You cannot make it with uranium. Uranium has only one application, which is fission. What is fission? It means that when actually uranium has three isotopes: uranium-235, uranium-238, and uranium-234. The main one for producing radionuclides is uranium-235. When one neutron attacks to uranium-235, uranium-235 will be excited in very high excitation. It will be uranium-236. It's very, very unstable. In very small amount of time, maybe 10 to the power minus 12 or something like that. It's fission. It splits into parts. One is small and one big. Actually, if we can say this one, these two elements or radioisotopes of those elements are created in one atom. If we have millions of atoms, we will have millions of these particles. First of all, we will say them fission fragments. Fission fragments, after decaying of beta minus, they will become fission products. After serious decaying of beta minus and gamma, they become stable nuclides. And also it produces 200 MeV energy and 3 neutrons. So these neutrons go again to produce fission with the remaining uranium-235, and in this case we will have a chain reaction for producing neutrons. So the same neutrons in the reactor can produce radioisotopes for us, or radionuclides. In this case, you can see the main radioisotopes are produced in fission. For example, is molybdenum, iodine-131, and strontium-90, cesium-137, and so on. But one of the main products of fission is molybdenum-99, which is the mother of technetium-99. We will talk a little bit about it. Maybe Dr. Shivani will talk a little bit more than me in this case. Well, what is carrier? If you produce radionuclide, for example, by N-gamma reaction, if it is the target is an isotope of that nuclide, it will be with carrier. And in this, for example, if we say with N-gamma reaction, either it goes to be radioisotope, but with carrier. It will be excessive activity very long. But in this case, you can see if you can have this reaction, N-gamma reaction, for example, gadolinium-160. By reaction of N-gamma, it will be gadolinium-161. By beta minus, it will become terbium-161. It can be for many other reactions for this. It is better to be the target to be enriched. In that case, will be specific activity will be very high. But if it is fission, its specific activity is so high. Actually, radiopharmaceuticals have two uses: diagnosis and therapy. We will start with diagnosis. Because gamma emission and positron emission are only photons, they can be used for diagnosis of the diseases, cancers, heart diseases, skeletal. For this purpose, most common diagnostic radionuclides are this one: technetium-99M, gallium-67, indium-111, fluor-18, thallium-201, and gallium-68. The most important one is technetium-99M. I will talk a little bit about that, which is daughter of molybdenum-99, and it is reactor produced by generator. Gallium, indium, and fluorine is the most useful radiopharmaceutical for diagnosis of brain and heart. as FDG, fluorodeoxyglucose. And gallium is also from cyclotron, and gallium-68 from the generators, germanium-68 and gallium-68 for PET imaging. Well, I want to tell you a little bit about technetium-99m. It is the unique radioisotope or radionuclide. As I told you, about 80–85% of the diagnosis of diseases are being done by technetium-99m. Very brilliant radionuclide. Decay properties, 6 hours. Very useful time for diagnosis of diseases. 140 kilo-electron-volt, energy brilliant because it is very useful to get radiation from it, and also it is not very dangerous for radiation damage. Production method is weekly, molybdenum technetium generator, and main application, can you see it? More than 80% of diseases are being diagnosed by this radioisotopes. 6 hours physical half-life means that a technician or a physician can do many experiments on him in 6 hours time, and it is not very long because of the radiation damage. So this radiopharmaceutical, which is being made by technetium-99m, very useful radiopharmaceutical for diagnosis of all cancers and also heart and skeletal. But to producing of technetium-99 is being done by 2 methods. One of them is gel moly generator, which is being done by molybdenum-98, well, reaction molybdenum-98, engamol, molybdenum-99, to which spectral activity not very high, it's very low. So, what the fission moly generator is very useful with high specific activity because it is produced already active atoms in that, or nucleus. We have done some work about gel moly generator in our laboratories some time ago, and you can see it. It was called Jobber Tech, it's a brand name. And now, at the moment, we are producing in a Pars Isotope company by fission moly generator. And because of the specific activity so high, so we should use fission moly generator. As you can see here, the main countries producing technetium-99m, and you can see there, for example, Netherlands, Canada, Belgium, France, South Africa, Argentina, and others. We also are from the others one, you can see there. And the users of technetium-99 or generator molybdenum-99, technetium-99m, United States, Europe, South Africa, South America, and Asia, and other countries like that. The amount of generators, the number of generators you can see here in the table, you can see in this slide. Altogether, 12,000 curie per week of molybdenum is produced in the world, and we produce about 120 curies of molybdenum in a week in Iran. It's about 250 nuclear medicine centers are use this one, and about 1 million people can use this amount of technetium in our country. Well, it's technetium-99 itself cannot be used directly in the body. It should be combined with other chemicals, or we call it kits. For example, if it is for use for heart, it should be technetium-99m, MIBB, we call it MIB. Or for example, if it's body scan, we can use it technetium-99 MGP, and so on. So as I told you, it is just like a man who carrying something in his hand. That thing in his hand is technetium-99M, and the man is maybe MDP, DMSA, and so on. So it can go anywhere we want, and we can check it after that by SPECT or gamma camera. And radiopharmaceutical, you can see it like this. So many. I think at the moment we can produce about 25, more than 25 kits in our laboratories in our country. It can be used for those patients. So after that, some radiopharmaceuticals for therapy, some cancers, and it is very useful. The therapy is different from diagnosis. In diagnosis, we can use only gamma, or maybe electron capture, or electron plus. In that case, we can use it for diagnosis. But for therapy, we cannot use gamma irradiation inside the body. They are use or alpha particles or beta particles. You can see here the number of radionuclides are being used in our country and in the world. In this shape, you can see iodine-131, the main one, because of the cancer of thyroid and anomalies of thyroid. Iodine-131 is used. After that, yttrium-90, lutetium-177, samarium-153. We are one of the main countries producing samarium-153. It is produced about 5-6 years ago. Actually, before strontium-89 as chloride was being used for the therapy. But at the moment, samarium-153 has been exchanged with it. And very, very useful for skeleton especially. You can see from this picture. Iodine-131, you can see here, as I told you, very important. Its half-life is 8 days. With high energy betas for cancer of thyroid and some gamma energies for diagnosis, actually. Actually, we can use iodine for diagnosis and therapy. It's very important. In fact, iodine-131 can be produced by 2 methods, 2 reactions. One of them is thallium-130, N-gamma, thallium-131, 2 iodine-131. But the most important one is fission. As I told you, fission is very, very important. One of the main products of uranium fission is iodine-131. Very, very important. Actually, for treatment of thyroid, the main and only pharmaceutical for it is iodine-131. You can see here how they use maybe iodine-131 used as sodium iodide only for thyroid. You can see it there in the beginning of the table. And after that, you can see another compounds of iodine-131 for so many diseases you have seen here. Lutetium-177 is another radionuclide, very important. It can be produced by 2 routes. One is lutetium-176 N-gamma, lutetium-177. It is not very high specific activity, but the better way to produce it, the better reaction is terbium-176 N-gamma, ytterbium-177 to lutetium-177. We have done it also in our laboratory by our pharmacists, by our scientists, and it's very important for us and for the world. You can see all the chemicals and keys can be used by with lutetium-177, and it is commercial use for treatment of the diseases. Another one is yttrium-90, which half-life 64 hours, but the energies very high energy yttrium production method. Again, is this one. You see, one method is yttrium 89 and gamma yttrium 90. Its rescue activity is not very high in that case. But if it is as a generator, because yttrium 90 is also from another fission product. You see, fission reaction is very, very important to produce neutrons and produce many kinds of radionuclides to be used for diagnosis and also for treatment. You can see here yttrium 90 is very, very important, but it is not produced in a time, for example, a week or so. It should be produced in nuclear power plants. In the processing, you can get yttrium 90, and after that, you can get yttrium 90 from that. We have done. Also, we get some yttrium 90, and we got yttrium 90 from the generator. You can see also here yttrium 90 with chemicals and many keys to be used for many diseases. But this one is very, very important, the samarium 153. It's a revolution in the radiopharmaceutical industry, especially for us, because it was the first time samarium 153, one of our brilliant students for me and also very good scientist of this country. I'm going to say his name really. But it was produced from, and it was used for all patients in the hospitals and nuclear medical centers. As you can see here, there are two routes actually. It is written here only one route, but I think and I imagine I have done some, but not so much. One route is samarium 152, but it should be enriched, you see, for M1 to get samarium 153. Another route is fission, but fission yield is not very high, so it is better to produce like this. Samarium 153 is for skeleton and many other diseases. Very, very important. This samarium 153, and because because this is very important, we also produce in our nuclear reactor this samarium 153. Another important therapeutic radiopharmaceuticals are alpha particles, alpha emitters, very important. You can see in this table, you see 2-3 radiopharmaceuticals very important. One of them is very important, radium-223. Actually, I'm going to tell you this, the route of production of radium-223. You see, it is actinium-1225 actually. After that, I will talk about radium-123. Actinium is produced from either thorium-229 or radium-226, like that. It is very useful for some of the diseases. You can see here production size, increase in transferring elements, Institute of Physics and Power Engineering, and so on. They produce this radiopharmaceutical for therapy. But this is again, it can be used for some diseases, kits and some chemicals like that. Again, you can see actinium here, and another one is astatine-211. The routes of production is like that, you can see here. And also it is being used for therapy of some diseases. They are actually, especially for cancer diseases, metastasis of cancers, especially for skeleton. But again, you can see here some kits of the astatine-211, and very important. Again, you can see here. This is lead-212. Not being used so many, but it is useful for at the moment it is for clinical trials. It is not being used for therapy at the moment, but it is for clinical trials. This is the most important one. I want to talk to you this one. You see, radium-223. The route of production is this one. radium-226, if it is the reaction with N-gamma, it will be radium-227 by beta minus actinium-227, and by beta minus thorium-227 by alpha radium-223 as a generator, you can see here. Why it is very important? It is in the periodic table similar to calcium because it sits in the skeleton. This is the first one. The second importance is this one. Radium-226 comes from uranium-238 in a chain reaction, in natural chain reaction, chain decay from uranium-238. Uranium-238 exists in the world so much, but it is very difficult to get 226 from it because the amount of radium-226 from uranium is so small. For example, I imagine, for example, if you use maybe 10 tons of uranium-238, you will get only a few milligrams of radium-226. So it is very difficult, but very important. And also the world is working on this radioisotope. We also working on this. So I hope one day we will get this radioisotope. And also it will be very useful for the cancers. So what is radiopharmaceutical in Iran? You can see here from 1970, Radioisotope Center was established in Tehran University a long time ago, 1981. You can see here, Establishment Research Center, 2006, Establishment of Research Institute, and 2012, establishment of private company Price Isotope, and at the moment, construction of a very big laboratory for producing radiopharmaceuticals. But I want to say something to you about 2012 and after, before that, 2006. When Nuclear Science and Technology Research Institute was established, we were in sanction, unfortunately. Europe didn't allow to come our generator from Belgium or other countries, so we started to work with ourselves. In 4 or 5 years' time, we worked, but our route was gel moly, and we produced molybdenum from molybdenum, national molybdenum. So specific activity was not so hot, but we could treat all hospitals and patients with this radiopharmacy. We are proud about it. About 5 years we worked about it, and we are proud about it. So how many nuclear medicine centers are in Iran? You can see here about 210 specs, 6 specs CT, 10 PET CT, but unfortunately we have no PET MRI. As I told you, because about 1 million patients are being used by technician maintenance, and also about 300 patients are being treated by iodine-131 in the world, in our country. You can see also nuclear medicine in Iran like this, number of nuclear medicine centers. In 1990, it was 10 only, less than 10, now 224. And number of PET centers, we have only 14 at the moment. Nuclear medicine centers, as I told you, it's about more than 200. The last number was about 250, I was told. Weekly producing more than 400 generators for it. And also we have iodine-131, more than 35 couriers per week. It's very important for our patients about that. And also weekly use of lutetium-177, about 20 couriers per week. And this is the building we are, this is the building we are construction for GMP, and also we will do our work in radiopharmaceutical protection in this building. Actually, I would like to thank IAEA and AUOI for supporting of this building for producing of radiopharmaceuticals. This is the building you can see here, a big building with so many laboratories we will have there, and we will have R&D department and also producing of radiopharmaceuticals there. Where you can see here providing services to patients. Iran is now positioned providing almost all national radiopharmaceutical demands. This is we are proud about it. Iran is one of the countries recognizing supply medical radiopharmaceutical exporting. Actually, we export some of our radiopharmaceuticals to other countries. Not very so many, but we export them. And you can see here, non-carrier added radionuclide produced in Iran. Tritium, holmium, promethium, terbium-161. And this is technetium, molybdenum technetium generator you can see here, and the laboratories are producing them. And these are the name of radiopharmaceuticals produced in Iran, are being produced in Iran. And this is the last one. At the end, I would like to thank IAEO and AEOI, International Atomic Energy Agency, and our colleagues in Vienna. They're just listening to us. And all the people, all the students, all the researchers are listening or speaking. And also, I would like to thank AEOI, Atomic Energy Organization of Iran, and Nuclear Science and Technology Research Institute, and also my colleague Yasser Khasisas, who advised me to do this work anyway. And I would like to thank you. And also Umid Afshe, one of my best friends here. But I don't want to give the other names, you see. You will hear Dr. Shirwani better than me. She will talk better than me. She will give you better than me. And she will deliver brilliant information about radiopharmaceuticals because she's a very good chemist, actually. Thank you so much for your attention. I hope you will have a good day. Bye-bye.
Thank you, Professor Ghanadi. Thank you for your informative presentation related to radiopharmaceutical. And we saw that this is the very important application of nuclear technology in human life, in treatment and also for diagnostic and imaging of human body. So we have enough time to Ms. Marina, if it is better to continue, or we have Q&A session now and then continue with Ms. Shirwani.
Up to you, Yasser. You can go to the next if you feel it's related, and then we handle all the question together.
Yes.
However, I see there is already hand raised for question.
Okay,
What should I do?
It is better for after next presentation, okay? Yeah. So at this time, I would like to invite Dr. Shirwani to provide his speech. Thank you, Professor.
Okay. Hello, everybody. Good morning, good afternoon, good evening from worldwide. I want to thank you all for joining this webinar and allocating your precious time to us to talk for you. And I actually want to thank Professor Ghanadi for the beautiful presentation that he made and the good things that he said about me. He actually is a great human being, not also a great scientist and a great radiochemist and a great teacher for us. He is also a great human being that we are learning from him a lot. Okay. Okay, this is Simin. I'm working as a member of scientific board in NSDRI. and I've graduated from University of Tehran in 2008. I've got my PhD in analytical chemistry, and after that I joined the great team in NSCRI who were working on the preparation of radioisotopes for medical purposes and also the preparation of radiopharmaceuticals. And during these years, I've been working as a member of this team. Okay, to go through the slides, first of all, I want to have an overview of some terms like radionuclide, radioactive decay, radiopharmaceuticals, and half-life. From the presentation that have been presented before me, beautifully, you had the explanation about the radionuclide, that is an unstable nuclide or isotope that for being actually stable decays in some modes, like sending out the alpha radiation, that is 2 protons and 2 neutrons, or sending out beta emission, beta minus or beta plus, which beta minus is killing the tumor cells, and beta minus what?
1 minute, please.
Okay.
I think it is some technical problem.
What is
The
it?
slide cannot change. So please.
Okay. Is it better this small? Okay, the other modes of the actually emissions that happens through the radioactive decay is gamma emission or gamma radiation. That because of the some special properties that gamma emission rather than beta emission or alpha emission has, can be used for diagnostic purposes that can be explained later on. As was explained by Professor Annadi, a radiopharmaceutical is composed of 2 main parts, a radioactive part that depending on which emission it has, it can be used for therapy or for imaging, meaning the diagnostic purposes in the nuclear medicine. And the targeting moiety, this targeting moiety actually determines the role of this radiopharmaceutical, if it's used for therapeutic application or for diagnostic application. And also, it also can determine that which part of the body this radiopharmaceutical is going to. And this part that is named linkering here is very important, because in one hand, this linker has the functional group that can complex with this radioisotope, and the other hand can be conjugated to the pharmaceutical part that is the targeting molecule. This targeting molecule, as was explained for you, can be antibody, peptide, or something like that, or small inorganic molecules that by having some special heteroatoms in its structure can carry these radioactive isotopes to the target site. And about the half-life, you know that the required time for the amount of the radionuclide to reduce to its half amount. In here, we can see different types of radiation, electromagnetic radiation, that encompasses different range of energies. The shortest wavelength goes to the gamma ray and then the X-ray. These two electromagnetic radiation can go through the body and can be used for diagnostic purposes. For example, if I want to talk about the gamma radiation and comparison with X-ray radiation, because we can actually send the radioisotope that emits gamma radiation inside the body using a radiopharmaceutical, it can be used for imaging the physiological processes, meaning active imaging of the body. Or about the X-ray actually imaging, because it is used for example, for the anatomical structure, it is somewhat different than gamma ray. And then we have ultraviolet that is responsible for the tanning. Some girls may understand me. They go to the ultraviolet, they go through the ultraviolet radiation to be tanned and have a darker skin. Okay, then it's the visible radiation that is from violet to the red color that is actually seen by a human eye, and then we have infrared, and then microwave and radio waves that is used for the communication or for the sending some messages. And in here, in the bottom of the slide, you can see the approximate scale of the wavelength. You can see the wavelength of gamma ray is about the atomic nuclei, and when it goes to the higher wavelengths, it's like a scale of a human being or buildings. About two of these radiations are called ionizing radiations because they can lead to ionization of the nuclei, the gamma ray and X-ray. But in here, we have other emissions, the ionizing radiation that's composed of alpha particles and beta particles. That the power of ionization of the alpha particles rather than beta particles is much higher. We will go through that and I will explain why is that. And then gamma and X-ray that I was explaining before that, because it can go through the human body, it can be used for imaging and actually for diagnostic purposes. Here we have a comparison of alpha particles and beta particles. And what is the difference between these two particles? Both of them are used for treatment of the cancer or tumor cells. But what is the difference between these two particles? Alpha particles, which are composed of two neutrons and two protons, are actually helium nucleuses that are traveling in the tissue or space in a short path length, and it leads to delivering high amount of energy in that short path length. Like they have a linear actually energy transmittance of 60 to 240 keV per micrometer, in comparison with beta particles that have 0.2 keV per micrometer. So if you want to have a localized high energy treatment, you can use the alpha particle or radiopharmaceutical that actually contains an alpha emitting radioisotope. And about the DNA damage, if you want to compare these two together, the DNA damage that is resulted from alpha particles is actually irreparable. What does it mean? It means that when it delivers high energy in a short path length, it can destroy the double-strand DNA in comparison with the sparsely ionizing beta particles, which will destroy just small part of the one strand of the DNA, which can be repaired. And about the photons, gamma rays, I also said for you that it's used for imaging. In here, we can see an illustration of forming a radiopharmaceutical in a simple way. We can see a radionuclide which emits alpha, beta, gamma, or Auger electron or something else is used for both purposes. And in here, we have an analog of natural compound. In here, we have a natural compound, in here, analog of that. It means you can use the natural compound itself or an analog of that. And what is this? This part goes through the body and finds the target sites on the surface of the tumor cells. And it can attach this radionuclide to the surface of that tumor cells. So you can use the emission of this radionuclide for therapy or for imaging. Imaging meaning what? Diagnosis. Yeah. And here we have the radiopharmaceutical. Okay, we said radiopharmaceutical can go through the body. It goes through the body, finds the target sites and attach to that. But what is the difference between the nuclear medicine and the conventional medicine? When you have conventional medicine, most of the time, almost most of the time, is used for diagnosis, like X-ray imaging or CT or something like that. But when you had the diagnosis, after that, different pharmaceutical is administered to treat the patient. In here, we have a radiopharmaceutical that goes through the body. Not only it specifically target the pathological actually tissue and used for image, and after that, when you find the pathological tissue, meaning the tumor cells or the sites that is full of the cancerous cells, then same radiopharmaceutical, by changing this part that is called radionuclide, and it can be alpha emitting or beta emitting, can be administered to treat the same part. So there is another difference, that these radio actually pharmaceutical in nuclear medicine can record the physiological changes, okay, but the conventional imaging can use the anatomical changes, meaning this is dynamic and this is static. Okay, here we are talking about the concept of theranostic, and it was started from the 1940s, when for the first time radioiodine, actually 131, was used for imaging of the thyroid, and after that, for the same target site, it was used for the treatment of that. What does it mean, the theranostic? Theranostic or diagnostic is the actually method that is a two-in-one fascinating method that is used for personalized medicine. What is personalized medicine? You see, when I use some radioiodine to diagnose, after imaging that part, to diagnose a cancerous cell inside the body, here thyroid cancer, after that you can use the same molecule for the therapy of that cancer. The combination of these two, meaning diagnostic or imaging and therapy, is called theranostic. So this is called theranostic, and it means using a same compound in here about radioiodine, because we are going to talk about another pairs. We did diagnosis, and after that the treatment. It is called theranostic, and it is important because when you want to administrate some, for example, radiopharmaceutical for a specific patient, you have to be careful. It's not useful these days. For example, if someone is 70 kilogram, you have to administrate 70 millicurie for that. No, it doesn't work like that. You have to be careful about that, about the cancer stage that the patient is, about even the sex of the patient, even it's male or female, and the age and the type of cancer. All of these things should be considered. And using the fascinating theranostic actually approach, we can do that. And it is called personalized or precision medicine or nuclear medicine. Here there is a schematic diagram of how the diagnosis phase is performed. After preparation of the radiopharmaceutical regarding this radionuclide, which is used for what? Diagnosis, yeah. It is administered by intravenous injection. It can be inhaled like xenon 133, that is inhaled, and an image of the lungs can be recorded, or ingestion, an edible capsule that contains some radiopharmaceuticals inside. After that, as it has these targeting moiety, it goes through the body, find its site, and after that, you can record an image. Here, you see, it goes through the blood flow, and via normal biodistribution, it goes through the body, finds its site, and after that, because it's emitting some ionizing radiation that goes through the body, comes out. For example, if it's beta plus or gamma emission, PET or SPECT images can be recorded in here. So the physician looks at this image, and he or she diagnoses that, for example, the abnormality is here. I can work on that. Here is the therapy. Next phase, the patient that, look at this, when you use the therapeutic radionuclide in here, for example, alpha emitting, beta emitting, Auger emitting, I don't know, whatever you want to imagine, you can administrate this therapeutic dose to the patient, and it goes through the body, finds the tumor cell attached to that, and after that, using that beta or alpha particles, it can be used for destroying the tumor cells through each one of that. For example, if is alpha emitting particle like bismuth 213 that emits alpha particles, as I mentioned earlier, it has high LET, linear energy transmitted in here, and the double strand of DNA can be destroyed, and these two parts of DNA cannot be actually repaired. So the apoptosis happens and the tumor cell kills itself. And here we have yttrium-19 that emits beta minus, and it goes through sparsely through the DNA and destroys one strand DNA, and it is repairable. Actually, maybe sometimes it's not, but in comparison with the alpha emitter, it is easier to be repaired. In here we have some helicopter in here. Maybe you're hearing that, I don't know. And we have technetium-99M that was fully explained by Professor Qannadi. I don't want to go through that, but using this pharmaceutical kit that is determining the role of this technetium-99M inside the body, it can be used for myocardial imaging. It can go through the brain using something that has some glucose in its structure, and so on. It depends on the pharmaceutical kit that is used in here for radio labeling. But what is the pharmaceutical kit? Maybe some students are here. What is she talking about? The pharmaceutical kit contains that molecule I told you already. The natural molecule is analog or an inorganic molecule that can find targets inside the body. But there are some other things inside that. And this is, for example, like buffer or some additives that makes the reaction easier and makes the product more stable. Okay, the last one, Dr. Qannadi also talked about iodine 131. I don't want to go through that again, but there are some other radioisotopes of iodine, like iodine 123, 124, which are used for imaging purposes, and iodine 125 that is used for preparation of some eye plaques that is used for killing the tumor cells inside the eye. Last but not the least, gallium-68 and lutetium-177. This is one of the most important theranostic pairs that we already know that all around the world they are using this pair actually. Why gallium-68 and lutetium-177 can be a theranostic pair? You know, gallium-68 emits a positron that can be used for positron emission tomography, meaning for imaging. And lutetium-177 that emits beta minus can be used for killing the tumor cells, okay? But what makes them a pair? Their chemical behavior, the chemical, actually the similar radiochemistry of these two radioisotopes make them a pair. Meaning when you are using some biological molecule like antibody or some peptides or something like that, and when you use this linker that in here is a DOTA, this DOTA can complex with gallium-68 and lutetium-177 in a similar way. So the full actually chemistry, the full chemicals that was used for actually preparation of the diagnostic radiopharmaceutical can be used for preparation of therapeutic pharmaceutical. So these two are called theranostic pairs. That's all for today. Maybe if I'm invited again to talk for you, I will go through some other things. And thank you so much again for your time and have a good day. Bye-bye.
Thank you, Ms. Chirhani. Thank you for your nice presentation. So we have time to go to audience. If there is any question or comment, please raise your hand. Okay, Ms. Nadia Asari, can I manage this, Marina, or open the...
Yes, Yasir, you are the moderator, kindly.
Okay. Okay, Dr. Shahid, in comment in the chat box, ask about, please share the status of medical radioisotopes produced through accelerators. Professor Qannadi, may you...
Yeah.
About the status of medical radioisotope produced through accelerators.
Actually, as I told you, there are two routes for the producing our radioisotopes. One is reactor, the main one. The another route is from the accelerators. Actually, few radionuclides are produced in accelerator. For example, gallium-68 and thallium-201, krypton-85M, indium-111. These are produced by reactions as PN, proton-neutron emission, or for example, PPN, P2N, and other, or for example, by deuterium. Actually, at the moment, we produce by proton only in our accelerator. We have one accelerator in Karaj province for our cells. This accelerator produces thallium-201 and also gallium-68 and krypton-85M, and they are being used in our hospitals in the country. If it is the question,
thank you.
I answered any of the question. I am here.
Okay. The next question, yeah, Miss or Mr. Muraginesi? Yes.
Yeah, it's during your presentation, you spoke about the diagnostic radionuclides, and one of the radionuclides you spoke about was technetium-99. About the production, why is it that most of the methods, or why is it that technetium is widely produced by generators? Is it for convenience, or maybe it's cheaper? Or let me say, is it possible to produce technetium by means of a cyclotron? If it is possible, what are the target materials? Thank you.
Yeah. To produce technetium-99M, the main route is by generator, molybdenum-99 to technetium-99M. And it's being done in all over the world at the moment, in Belgium, Holland, and South Africa, Russia, and Canada. And but there are some routes to produce technetium-99M directly by cyclotrons or accelerators, but it is not at the moment in industrial stage, and it needs a long time to go for that, because the need for technetium-99 is so much, and it is very useful at the moment to produce this technetium by generator. This is the second. This is the first one. Secondly, I want to tell you something. Because it is generator, and molybdenum has 2.7 days of half-life, and technetium 4.4 hours half-life. If we produce technetium by cyclotron, it is very difficult to keep it for a week in all the countries and all of the sites on nuclear medicine centers. It's very difficult because it decays very soon. But actually, because molybdenum has about 64 hours half-life, so we can use it in a week or so, and it's very important at the moment to use generator. Actually, if we use it, for example, in a city or in a very nearby cities, it is very useful to use this cyclotron. But at the moment, it is not. I think it is not very useful for that.
Because of time.
Because of time. Okay. Because of half-lives.
Because of half-life. Okay. Is there any question? Yeah. In case of miniature neutron source reactors, is it they can produce also radioisotopes for medical purposes?
Actually, to produce radioisotopes, actually the cross section and also the flux of the neutron is very important. I think I am not expert in reactor. I think small reactors cannot give that amount of neutrons. It's better to use, for example, to produce molybdenum, at least you will have 5 multiplied to 10 to 13 neutron per centimeter, square centimeter and second. It is not, I think, enough fluxes in small reactors. it's better to use it. Reactors such as, for example, Tehran reactor is about 5 or 10 megawatts power.
Also, I think the continued operation is also the
Yeah, that's right. But the flux is very important. I think they don't have that amount of flux for that.
Okay. Could you please about the countries Iran exports the medical radioisotopes?
I think a few countries and agencies knows these things. I think they have exported to India, I think in Pakistan, and also nearby countries, and nearby countries, Iraq.
Okay. Is there any questions or comment by participants? Okay, if no, please, if no, thank you again, Professor Kandadi and Dr. Shirwani for their speech through this webinar. Thank you all, and I appreciate your participation. As I know, the recorded video of this webinar will be accessible through the ANET website. Also, I would like to invite all of you to follow up and join the ANET social media account in Instagram and also in Telegram. I
Yes. I want to say something.
Yes.
Mr. Misha.
Yes.
Misha.
Yes. Ms. Marina.
Marina Misha.
Yes.
Mr. Misha Marina.
Marina.
But last time I told you that my name is Muhammad, okay? And I had so many friends from Malaysia when I was in England. And I was studying there in the university in England. And I had so many friends, colleagues from Malaysia. And they were very, very nice people, actually. Very, very good people. And I remember all of them. I don't know, you know their name or not. I think they have retired. They have retired at the moment. But if you can, if you know them, please send my regard to them. Dr. Malik, Dr. Zahraddin, Dr. Khairuzaman, Dr. Yusuf. Yeah. And because Khairuzaman was sometimes in the agency, I think. The Malaysian, yeah, from Malaysia. But anyway, if you can see them or you can talk to them, please send my regards to them and say, Muhammad, send a regard to them. Thank you so much.
Thank you.
Thank
Okay,
you, and pleased to know that you have many good friends from Malaysia, and I know some of those names. And inshallah, whenever I go back to Malaysia, I will try to reach out to them.
Thank you so much. Assalamu alaikum.
Thank you, Ms. Marina. If you have any closing remark for Xiaojing or you?
I think maybe I'll invite Zhao Jing as the as steering committee member who is responsible for the webinar. Xiao Jing? Xiao Jing, you're muted.
Thank you, professors. I mean, I was just typing in the message box I want to show my thanks to the two professors. Thank you for your very comprehensive and informative presentations. And thank you for your contribution to this webinar. As Yasser said, this webinar video will be uploaded to ANET website, and I'm sure you can find more information, more webinars from our website. And this can be very good materials for expertise from all over the world to learn. Thank you very much. And please pay attention on our next webinar in June, and there will be information about it on our website and our social media. Thank you very much.
Thank you, Xiaojing.
Thank you.
Thank you.
Bir kommentiniz neler?
Thank you and bye everyone.